This is all of us. We're the biggest group as far as I know. So we looked at a lot of different environmental aspects of Boston Way. Our major focus was hydrology, green infrastructure and how that combines with your stormwater runoff, and then we also did a floodplain analysis for like building materials. So it's all kind of within the environmental realm. First question is why stormwater management? This is Cincinnati, right here. When it rains, basically raw sewage just goes straight into the Ohio River. That's how it works. The EPA charges you a fortune for that, and now they're in Cincinnati's officially under consent decree to clean that up and make it not happen. Currently, there are over 100 combined sewer outflows, like discharges every year, and the EPA allows 3. So you can see why that's kind of a problem. A lot of the issue is actually a lot on the west side, but you guys will still encounter it on the east side. This is kind of the approach that we took with Boston Way. So we wanted to look at a little bit more, like as Boston Way, a little bit more than just transportation. We know Boston Way is really about the community. It's about biking. It's about light rail. It's about moving away from your car. That's the point. Education. We think Boston Way would be a perfect place to showcase some green roofs, some green infrastructure, some ways of doing things a little bit different in Cincinnati, and will be an ideal, like a showcase to make that happen, because people are traveling along it, they see it, and then about transportation, obviously, and then kind of casting a vision for the rest of the development that can happen in Cincinnati. I'm not going to read this to you guys, but these are our project deliverables. We had a lot. We got 3 separate groups under our team, and this is kind of all the things that we went through. If you want, I'm more than happy to email this presentation to you guys later, and you can look at all of them. But we just want to put those up there so you kind of understand what we were shooting for. We'll start with Chris. He's going to go over the model that we developed.
For hydrologic analysis, we took the approach of using TR55 analysis. That's Technical Report 55. It is published by the USDA, NRCS, Conservation Engineering Division, a whole bunch of people. But basically, it's an approach to do a hydrologic analysis, give you peak flows, watershed time of concentration, basically everything for small urban hydrologic analysis. For the tools we used CAGES to get our topography. We used the USDA Web Soil Survey to understand the soil groups affecting the hydrology, as well as Autodesk storm and sanitary analysis for creating the actual model. Now this is the overview of our model. There are 36 individual watersheds, each classified by the subbasin, the icon, and each attached to an outfall. These are all delineated from 2-foot contours from the CAGES, and basically each watershed is defined by the curve number and the time of concentration, which I'll go into how we got that. For example, let's look at our 19th watershed, which I dubbed West Erie. Each one, you can see, is attached to an outfall down here. And this panel up here basically is where we put all of our data. There are 3 tabs. One is for physical properties, which is just the watershed area itself. And then there's the time of concentration tab and the curve number tab. So, in the USDA Web Soil Survey, we delineated the watershed here to get our area of interest. As you can see, there are different lines indicating the different types of soils in the area. And each soil has a hydrologic soil group. And for pretty much all of Boston Way, they end up being D. D typically yields you high runoff. It's not very, we don't see a lot of abstraction in soil group D. And so each curve number for the watersheds are calculated from these percent of areas here. So in this particular watershed 19, we have all soil group D with these sorts of percents. So we know that 86.8% is urban residential, 13.2 is good wooded. This is just based on the land use. So knowing that we have residential here, residential is 92 curve number because it's group D, as well as 8 acre or less residential. Putting those into the spreadsheet will give us a weighted curve number at the end based on percent averages. Now we have to get time to concentration. Time to concentration is either based on the flow type, essentially. You have sheet flow or shallow concentration. Sheet flow has a maximum flow of 300 feet. By then it turns into shallow concentrated flow. And for this particular watershed 19, the topography blends directly to shallow concentrated flow, not sheet flow. So what you see here is an example of how we calculated it. We take the flow length over the entire watershed, which has a slope of, at least in this case, 0.88%. It's unpaved, and the program just calculates our time of concentration in minutes. Using those characteristics for each watershed, we then put a rainstorm into it, which is shown by the rainfall hadograph here. This one is a 100-year storm rainfall hadograph for Hamilton County. By putting the rainstorm in, the program will then simulate it, give us our direct runoff hydrograph, and in this case, our peak is 12.2 cubic feet per second. That's the basis of our model for all 36 watersheds. Now that was pre-construction. We're looking at post-construction. We addressed the worst-case scenario. The worst-case scenario, we just figured everything is paved for our watersheds. This is going to give us the maximum amount of runoff we could ever consider. And to do that, we consider all curve numbers 98 because, as you can see here, for paved, curbs, and storm sewers, all 98 at Toker deep. So that's our pre-construction, post-construction model. However, we did also use green infrastructure in our analysis as well. So to figure out how that works in, we have our green infrastructure team.
So, idea of green bridges is pretty much using green walls on fences, which are required for safety. Green walls, they're kind of new to industry and they don't have any standards, so we're free to do whatever we want, which is great. For this analysis, I estimated the cost of green walls, and it came up with optimum design for the budget. And then I calculated water demand to make sure we have enough water from a runoff to support the vegetation on the ridges. So green walls, there are two types of green walls. You have a green facade and live wall. A green facade is pretty much systems for climbing plants. Live walls, they support all types of vegetations, and they're made out of everything made clay, metal, concrete. So that was my initial design. I wanted to put a live wall on I-71 on like 3 big bridges in the area. So I wanted to have a live wall on the outside, on the inside, and the same thing on the other side. And then you use it as an advertisement to generate some profit. Unfortunately, this design right there would be over $1 million, which I think is a little bit expensive for the project. So I did some estimating. So the prices which I came up with for live walls, and that's the prices to buy them, to install them, to vegetate them and everything. They range between 150 and 120 per square foot. And then I did some estimating for green facades. If you're into immediate gratification, you can go with pre-grown at $75 per square foot, or you can grow yourself on any structure, and that gets cheaper. Like this one right there is it was done in Chicago, I think in the zoo, and they pretty much landed at the bottom of the structure. It was $2 per square foot. That's very cheap. So that's what I'm proposing. Excuse the graphics, it's not my strongest thing. So I'm proposing to plant an ivy along the fence in continuous soil containers and use a live wall as a section for advertisement. Well, you see that PNC, it could be P&G or whoever's willing to pay more. The cost for each bridge are estimated there. If we're gonna plant ivy by itself on the fences, it's gonna take a while for it to grow, but it's gonna be so cheap, it's gonna be amazing. So basically it's gonna be $40 per linear foot, which comes down to be like $4 per square foot of fence, which is not bad. So then I had to estimate how much water will our green infrastructure need in order to be, in order to sustain itself. And honestly, you can't really come up with a demand if you don't have specific soil and specific lands in mind. So I came up with a range. Here's the formula I used, and the formula depends on evapotranspiration, however you say it. So basically it's a sum of evaporation and plant transpiration combined, and I just assumed that our potential evaporation will equal to our evapotranspiration, and that this condition is true if water supply is empty. So this was an overestimate big time, and as you can tell, we're within 2%. So basically, there is a percentage of how much we need and how much we got, and I can repeat again, it's overestimate, and we're good to go on every big group.
Okay, so I looked into integrating green roofs along Boston Way, and basically where these would be integrated would be the large station hubs and the small station shelters. And I'm looking at the station hubs as being the Xavier area and the Red Bank Road area, and the 3 shelter stops in between would have smaller shelters. So there could be many benefits with integrating green roofs along this area. One that's been hit is stormwater mitigation. In the summer, 70-90% rainfall can be retained. And basically I would just slow it down before it gets into the storm sewer system so we don't overflow. Better air quality, it can filter pollutants from the air, extend the roof's life expectancy by 2 to 3 years, decrease energy demands by absorbing heat, and also by keeping the roof cool through evapotranspiration. And then also aesthetics. Green roofs would bring aesthetics to this project, and this is especially important in areas like Hyde Park, who the community was based on, or was built on preserving natural beauty. So here are some comparisons of the types of green roofs. You have your extensive and intensive systems, which are the 2 main types, and then semi-intensive is just kind of falls in between them. The main difference is basically just that one is deeper than the other. The intensive system is deeper and therefore weighs more, has higher loading, and you have more opportunities with different plant types if you're using the intensive system. So these are the recommendations we made. For the small shelters, we figured it would be about 4 to 5 inch extensive system, and it would look similar to the Philadelphia bus station, what they implemented there. And then for the large station hubs, it would be about an 8 inch intensive system, and it would be similar to the Arizona Transportation Center. So there are no ASTM standards right now. They're in progress for green roofs. However, companies do it kind of a case-by-case basis, and they generally follow the German FLL guidelines and standards. So I did kind of an estimate comparing different companies, and I went by the system cost, irrigation cost, maintenance, and that just shows the total upfront cost and then the total cost including maintenance basically after 1 year. And so then I did a cost comparison over 30 years for just the live roof system, and although there's a higher upfront cost, green roofs can pay off in the end. If you look at the replacement cost of roofs and then the energy savings, which I calculated from the Portland State University website, they kind of came up with a way of measuring the energy savings from a green roof by putting in your area and leaf coverage and your depth. And so, as you can see here, that the live roof system after 30 years comes out a little bit ahead, and so that just shows that green roofs can actually save money.
Alright, so let me take that and plug it into our model. There are 36 watersheds, and this is one of them. This is the Lexington Gardens area. We chose this because it's already one of the biggest chunks in Long Boston Way, and you guys already kind of have a proposed framework. We do at least half of it, kind of like in this garden, or mixed residential, like in the charrette. So we took that and put that in here as well. So this is worst case scenario right here. That's post-development 100-year storm, which is what you have to calculate and mitigate with Hamilton County Code. This right here is your allowable, that's your pre-developed. That's your pre-developed storm. So it jumps from here to here, which is a pretty good chunk. I mean, it's about 30 CFS. And then down here is what you're actually allowed to let out of your detention structure. So you're gonna need a big detention tank. But what the big difference here is that using a green roof, it doesn't drop the peak a ton, but what you need to look at is that what you have to mitigate is the volume under these curves. And I mean, that's done through the program. And if you go through here, it's the same thing Hyde Park Plaza, we did the same thing. But what this showed was, in the Lexington Gardens, before development, you already had 167,000 running off. After development, you had 187,000 cubic feet running off. If you use 50% green infrastructure and design it similar to what is already been determined in the charrette, where you have at least 50% of that watershed area covered in 75% vegetation, then you will actually improve it overall hydrologically. And actually, you know, this went up 20,000 and this drops 26,000 from your initial, like your right now conditions. With the Hyde Park Plaza, pre-developed, not a big change here, but just by doing a 2,000-foot green roof and a 2,000 feet of rain gardens or something else, the green infrastructure, you can get it right back down to pre-developed conditions. And what that means, basically overall what that means is you're no longer having to mitigate stormwater. So you're not putting in storm sewers, and you're not putting in underground detention tanks, you're not digging everything up. You know, it looks great, and you're not having to put in all that other annoying infrastructure. So overall, this is kind of what we came up with. I highly recommend that you just go and look at the poster after this, because that will make this much easier. But this is the map that's on there, and we kind of identified the regions. The red regions are where there's some major issues, like hydrologically, like where you're gonna actually need to do something. And then Eric did our cost estimate for all of this stuff.
Alright, so for the sewer, we decided to use a corrugated metal pipe, slotted drain made out of corrugated metal pipe. And there were some bids found online, bids that were awarded for corrugated metal pipe. And then we just took each one of those diameters and took the price times 2 to account for the fact that you need to add the slotted drain on top of it. So that's materials in the fabrication. And then for the vaults, there was a source that said $3 to $10 per cubic foot of storage for plastic and corrugated metal pipe. But we decided to treat vaults. So since concrete is more of an expensive material than both plastic and corrugated metal pipe, and it's going to be more of a simpler vault, we decided to go with the higher price range. And for rain gardens, there was a price range on the University of Connecticut. They had a price calculator for rain gardens, and it was $5 to $45 per square foot of rain garden. We decided to go with the $45 per square foot as the estimate because this is located on the rail line, so there was a lot of bad materials going through, so we need to excavate the dirt and replace it in order to put rain gardens down. Originally, I thought $100 per linear foot of laying the pipe for construction would be right, but then I remembered that was for sanitary sewer, and those are usually a lot deeper than what we planned on doing. What we planned on doing was putting the pipe right beneath the surface, so that gets rid of a lot of excavation costs. So I came up with $50 and talked to somebody that I know at the Metropolitan Sewer District. He said, yes, that I can't see it be more than $50. And for the construction contingency, we went with 10% of the construction cost, because that is also the normal percentage that the Metropolitan Sewer District uses. So the estimate that we went with was about $2 million, and after that, then we looked at implementing rain gardens, the price ranges. In Hyde Park Plaza, you can see the difference between there. The rain garden was actually cheaper for a small amount of area. I think it was about 2,000 square feet. And in Lexington Gardens, it was almost close to 20,000 square feet, and it was a lot more expensive. But the question that needs to be asked here is, how much do you really want to spend to mitigate the runoff? Because the rain gardens completely mitigate the runoff. And there are also some extra prices that go with this. There is 1 to 3% maintenance for pipes and vaults, and there's 5 to 7% maintenance for rain gardens, and that percentage is for construction.
All right, and this yielded our overall conceptual design to be implemented wherever you like, and this was help, with the idea of irrigation in mind, green infrastructure, rain gardens. So we have the rain coming onto the green roofs and onto the rain gardens / bioswales. It will trickle down and it'll be filtered. Now this isn't necessarily in all areas, but only where these rain gardens and green roofs are at. They get filtered. So I'm not filtering all the stormwater that ever runs on your property. I'm just filtering it where the rain gardens and the green roofs are. It gets filtered, it goes in this irrigation detention tank. When this fills up to a certain point, it will overflow to a detention structure depending on the size. This is just kind of a backup. But I haven't really worked out whether or not where that would end up going. Ideally, you wouldn't even need this because you would put in enough rain gardens to not need an overflow detention structure. Other than if your irrigation, this is going to take a mass balance. It goes to a pump, and then from there you can irrigate irrigate your green walls, which is a big thing, and then reuse it for your bioswales and your green roofs.
So since we're on the environmental team, we want to look at multiple aspects of the environmental aspects of Wasson Way. So while our working in the floodplain isn't directly related to hydrology as well or green infrastructure, specifically like hydrology and green infrastructure was interrelated, because it was an environmental issue, the floodplain is something that we need to analyze, especially because the portion of proposed Wasson Way is in the vicinity of the Little Miami River. So the first thing that we wanted to do was identify the floodplains in the area. Now to do that, what I did was contact the Federal Emergency Management Agency, FEMA. They put out a series of reports, NFIP, otherwise known as the National Flood Insurance Programs, which do outline the floodplains for certain areas. Luckily, this part of Wasson Way was one of those areas. Unfortunately, the lowest floodplain that they do show is a 100-year floodplain. I really looked at something lower than that, the 5-year and 10-year floodplain, just something not quite a size of a 100-year floodplain. So what I did was contact several agencies. Unfortunately, Marymount was primarily located. I talked to their planner, their city engineer. They didn't have any information on it. Luckily, I was able to get in contact with the floodplain administrator for FEMA for the city of Cincinnati, by the name of Tom McGuish. And I spoke to him. He worked down at the city permit office, and luckily he had one report, a report made by an insurance company to determine, for great purposes, what the 10-year floodplain was for this particular area. So by looking at this report and using Google Earth to determine the elevations, I was able to determine the 10-year floodplain for the area. And you can see that our proposed route from Wasson Way lies just up to the 10-year floodplain, or the fact that there's a 10% chance that this elevation will be exceeded every year. Luckily, what FEMA was able to give FEMA was the 100-year floodplain, or the 1% chance that this flood elevation will be at this rate or exceeded every year. Now, as you can see, our proposed route lies just within the 100-year floodplain. And finally, the 500-year floodplain was also provided by FEMA, or a 2% chance that this flood elevation would be in excess every year. Now you can see the summary of floodplains. I figured that the 10-year, the 100-year, and the 500-year floodplains really give us an overall feeling for what we're looking at in flooding emergencies. If we have a 10% chance, a 1% chance, or a 0.2% chance of these elevations being exceeded every year. Now, another one of our deliverables was to identify if any relevant soil conditions could tell us more about the floodplain, and if so, how it would be affected by the frequency of flooding. Specifically in the area of Little Miami, where these floodplains were so relevant, I looked at 3 different soil types where our proposed path crosses. As you can see here, they're identified as JU, GO, and BOE. And I got this information from an old soil survey put out by the Department of
of Agriculture, specifically for Hamilton County. Now, just a few things I looked at to gather more information was 2 types of charts that this soil survey put out. The recreational development for paths and trails, which did indicate that in 2 of these 3 areas there was already slight development. Otherwise, in the VOE, it did show that the slope erodes easily, which would be expected from the floodplain. Something else that I looked at was the building site development, specifically for local roads and streets. Now, under GL and JU, we do see that there is severe flooding indicated, which we would expect once again, as this is within the floodplain. One thing to note, under the VOE, there is a severe slope, which actually is expected because this is where the floodplain changes from the 100-year to the 500-year floodplain. So, marking off that area.
One of our goals with the floodplain group was to lay out the actual location of the path in our area of interest, which is the easternmost section of Wasson Way. So what we have up here is a line that has the same width as the path, 17-foot thickness, that goes through the floodplain. And the big consideration here is the proximity to the Little Miami River. So what we do, go to the next slide, is we want to have a stream buffer. And a stream buffer is basically a line that's parallel to the stream and it's a certain distance away from it. And inside the stream buffer, we're going to want to keep it vegetated. And we're going to want to put any of our development on the other side of the stream buffer. And what we have up here is a 50-foot stream buffer. Most of the design manuals that I saw used from the Ohio Department of Natural Resources used a 50 to 70-foot stream buffer. I thought this is a 50-foot right here, and I thought anything over that would have been just way too close to the development that's on Rooster Pike there. You go to the next slide. And right here, the red line is still that 50-foot stream buffer, and the yellow line is the path again. You'll notice that there's a couple areas, specifically right there, where the path goes under a bridge. That is like that for continuity of the path, and that's an area of interest that we'll talk about later. And another area of interest is right there behind, that's a Kroger's right there. And I really, for a number of reasons, I wanted to get some space away from Kroger's for the path. And so that's why it goes inside the stream buffer that I just mentioned. And another thing you'll notice is this entire path is pretty much going all the trees in the forest. So there's going to be a lot of considerations for construction and degrubbing and getting those trees out to put the path down. Cross section. This is a typical cross section, excluding the path under the bridge and behind Kroger's of what we want Wasson Way to look like in the floodplain. A couple of characteristics I want to point out. Because we're subject to the poor soil in the area, the minimum 6-inch thick gravel base will need to be thicker and more resistant to washing out, eroding away. Another characteristic is that I chose a 2% cross slope. This satisfies all the drainage needs of the path, and it also satisfies the ADA standard, which of course is the American Disabilities Act. Another thing is reforestation. I have the tree there. The trees cannot be at minimum 6 feet away from the trail, and for every inch thickness of the diameter of the tree, it needs to be that many feet away from the trail. The reforestation is going to be very important. It is the most cost-effective way to increase water quality, infiltration, and naturally maintain the floodplain as the most cost-effective way possible. And also we have the bioswale here. This will be the uphill side of the trail. So when water flows down the hill, it will hit the swale, and that will be mitigated to culverts that are already put in place for parking lots in that area. And then the other side of the trail runoff will go down the hill into the river.
Also with floodplains, we want to look at permitting. So as Anna said earlier, that actually Village of Marymount is part of the National Flood Insurance Program. They have been so since 1974. So basically the NFIP allows owners to purchase insurance for flood damage in the area. Permitting, there's 2 permits that I thought were necessary, and they were general individual floodplain development permits. For special flood hazard areas, as diagnosed by FEMA, you definitely have to have this general floodplain development permit.